We will continue ANOVA for another 15-20 minutes, then we will discuss MANOVA. We have seen the hypothesis testing using ANOVA, where we have said that all the means are equal and alternative hypothesis at least one pair of means are not equal, and using F test we either accept or reject the null hypothesis. For the problem considered, we find that the null hypothesis is rejected. So, in our case null hypothesis is rejected. Hypothesis is rejected. Okay. Now, we will discuss two things. One is that when we talk about towel, that is the population effect, that is for health population, we want to compute it. How to compute this towel? There will be two cases, one will be point estimation and second one will be interval estimation. What we have seen earlier for some population mean and difference between two population mean case. Okay. So, in this case for ANOVA, that grand mean, estimate of grand mean is the grand sample mean, then estimate of population mean is again the sample population mean, and estimate of population effect is your estimate of that is the population mean minus grand mean, which is x L bar minus x bar. Okay. So, this is what is your, I can say that point estimation. This is what is your point estimation. Now, you want to find out the interval estimation. What you will do? What you require to know? Like earlier, we can say that the towel, which is your x L bar minus x bar, this is a random variable. This is a random variable. The reason is both all are estimates only. So, if you know a random variable and you must know the that distribution of that random variable, and you must know the statistic and the sampling distribution of the statistic, then only you will be able to find out the interval estimation. In this case, towel cap or mu L cap, we want to know the interval estimation. In ANOVA, you have computed MSE. MSE is SSE by its degrees of freedom, that is n minus L. This is estimate of sigma square. Okay. What is this sigma square? You recall the Bartlett test, where we said that sigma 1 square equal to sigma 2 square, all population variances are equal to sigma square. So, this one is the estimate of sigma square. So, MSE, so we know MSE is known. Now, if I want to know what is the distribution of XL bar, then we will say this will follow normal distribution with mu L and your that sigma L, that's sigma XL bar square, this one. And you can remember that this will be nothing but mu L into sigma square by your n. Now, sigma square, estimate of sigma square is your MAC. So, I can say now then this is my mu L, can I write down like this MAC by n. Then what I am saying that XL bar is the health population mean estimated from the sample, and as it is an estimate, it is a random variable which follows normal distribution with mu L and MAC by n. Then I want to know the interval for mu L. So, you want to know the interval for mu L. It is similar to finding out the interval of population mean, what you have seen earlier using t-test and other things. Can you write down what will be the this side and what will be the right hand and left hand side? Can you tell me? So, definitely first will be the mean value, point estimate value. What is required to know? You required to know what type of distribution it is. It is basically we are saying that normal population, and we will assume that sample size is small. Then what you require to do? You require to use t distribution. Now, what will be the degrees of freedom for this in this case? In this case, you will find out the t distribution degrees of freedom will be n minus L. And I think you can remember the earlier case, when two population case we have gone for n1 plus n2 minus 2. So, here this capital N is n1 plus n2 up to nl minus L. So, the same manner this alpha by 2, correct. Then what you require to write down this, what is the else, that is the variance part. So, sigma square by n, instead of sigma square I am writing MAC by n. Then this side it will be XL bar plus T alpha by 2 n minus L square root of MAC by n, correct. So, this is what is the confidence interval for XL bar, where you please remember it is always confidence interval related to the population parameter, that is mu L. So, it is a confidence interval for mu L and the range is XL bar minus this quantity to XL bar plus this quantity. Okay. Another issue what you want to do, you may be interested to know that what is the interval estimation for XL bar minus XM bar, Lth population minus mth population. That means what I mean to say, you will be interested to know mu L minus mu m and mu L minus mu m less than equal to this less than this interval you want to find out, and this one XL bar minus XM bar, this is the random variable. Let me repeat that we are interested to know the interval estimation for the difference between two population mean mu L and mu m. We will be using the statistics XL bar minus XM bar. So, what you require to know? You require to know the expected value of XL bar minus XM bar. This will be nothing but mu L minus mu m. You also require to know the variance component of XL bar minus XM bar. This will be variance of XL bar plus variance of XM bar, and all of us know that this will be your sigma I can write L here, L square by NL plus sigma m square by Nm you can write. But here what we have considered that all the population means are equal and sample size is also same. So, we can write this one by sigma square by n plus sigma square by n, that is 2 sigma square by n, which is nothing but 2 MAC by n. Now, if you want to find out now that what is my mu L minus mu m, the interval, then you must write down that this one, this is the first part, then minus what is the, we again consider the same t test. So, we will consider n minus L alpha by 2, only thing change is instead of MAC by n it will be 2 MAC by n. See, the 2 is coming. Earlier for one mean case you have used MAC. So, 2 MSE by n. So, this side will be XL bar minus XM bar minus plus T n minus L alpha by 2 square root of 2 MAC by n. What will happen if your sample sizes are different? So, this quantity will not be 2 MAC by n. Exactly. So, for unequal sample size case, actual L bar minus XM bar minus T n minus L alpha by 2 square root of MAC into 1 by, suppose for the first one N1 or NL you write, second one Nm, because this L and M population less than equal to mu L minus mu m less than equal to XL bar minus XM bar plus T n minus L alpha by 2 into MSE by 1 by NL plus 1 by Nm. Okay. Now, see, we by saying this, what we are saying, it is 100 into 1 minus alpha percent Ci, correct. Is it true that it is 100 into 1 minus alpha percent Ci if I compare all the pairs?
No,
it will be reduced. So, it is basically we are talking about okay, two populations. We are not by saying this we are talking about only two populations. We are not talking about that multiple comparisons simultaneously. So, what is required? You require to find out that how many comparison possible, and then you have to go for Bonferroni approach. Okay. So, you can make it tighter by using Bonferroni approach. Okay. So, let us now again I will repeat one thing, that basically first is collectively you are rejecting or accepting null hypothesis where we are saying that all means are equal or one pair is different, at least one pair is different. Then when you find out that null hypothesis is rejected, you are finding out the point as well as interval estimation for the population means as well as mean differences. Now, you require to know that if sum of if H0 is rejected, then which of the pairs are different, correct. So, we will see here with an example. Now, see the same example again. We say that process A, B, C, the effect A's effect is 0.63, B's effect is minus 1.67 and C's effect is 1.03. If you sum total this, what is happening? How much it is? All effect sum will be 0. Keep in mind this one. Here it is basically rounding error is there. So, 0.63 minus 1.67 plus 1.03, that is 0. 0.01 or something is coming, but it is a rounding error. Okay. Then using the formulation, we have found out the confidence interval, that is 100 into 1 minus alpha percent Ci, here alpha is 0.05. See what is the value you are getting for A, it can be 0 to 1.27. That means almost 0, it includes 0, that means no effect almost. Second one you see, it is minus 2.30 to 1.04. Third one if you see, it is 0.40 to 1.67, that is the confidence interval for the individual effects. Then we will find out that what is the difference in the different population means. Okay. So, here first is the process effect and confidence interval for means, second one is the difference in population effect, and the differences are for A to B, that is 2.30, A to C minus 0.40 and B to C minus 2.70. What are these? These are the mean differences, correct. Now, using this formula again, using this formula, the second one as equal mean, the second one, this formula we have computed the confidence interval. Now, in the first case A versus B, the confidence difference in means, the confidence interval is 1.41 to 3.19. In between there is no 0. See, there is no 0 in between. That means there is you can see that there is a difference between A and B. Now, come A to C. You see A to C minus 1.29 to 0.49, in between there is 0. So, AC difference is not there or less. From statistical sense we will say it contains 0 means there is no difference. What about B to C? Minus to minus. So, it is there. So, now if we group, we can say that A and C, they are almost equal effect, but B is entirely different. That is what you want to understand. Okay. So, if you use Bonferroni approach, it will be little tighter, but there is many other techniques available like Taki criteria. I think you know Fisher LDA, linear discriminant analysis.
Can we use this for clustering?
Which one? This concept? Which one you are talking about? That grouping, that 1 and A and C and all those things. Clustering, see, ultimately some groups you are getting. Essentially clustering means from the data you want to group something. So, you want to find out, so okay, so I have different items I want to group. But here the primary difference is, it is not that you are your process A and process B and process C, you are talking about one observation from each of the processes. It is not, you are taking a large number of values or in terms of sample from the processes. So, essentially you are not grouping the items in that sense. Clustering is what? Clustering is, suppose I have several individuals 1 to n, then because depending on certain characteristics, let it be p characteristics are there, it may so happen that 1 to 5 these are making one group, rest is one group, rest is one group. Okay, that is the from individual observation point of view we will find out like this here. So, here also you can say, because what is happening here, it is basically instead of I, if I say the first one is A, second one is A, like this basically in 3 different groups are there. I think it is not fit for clustering. The reason is we know ABC. Clustering essentially, what with clustering you are saying, supervised or unsupervised one?
Unsupervised.
Unsupervised case groups are not known. But here we know that these the groups are there, A, B, C are there, but again with A, B, C you are grouping further. No, because clustering is very rich. So, we in clustering time you use either hierarchical clustering or K means clustering, C means clustering, that is their superior method. We should not go in this manner. But again definitely I can say you found out 2 groups, and that is why you thought in this line that can it be clustered, that is the message. Grouping is basically, here we are saying from mean point of view they are similar. Okay. Then you require to see that whether your model is adequate or not. How do you understand my model is adequate? First of all, you have to find you have to test the assumptions. So, under ANOVA one of the assumption is normality. How do you test normality? Any idea? Chi-square quantile plot is there, that is for multivariate case. Univariate case you can go for quantile, but that will be Z quantile. Otherwise simple PP plot, probability plot. Probability plot is there. Here what will happen in probability plot? I think you go through any basic statistics books, you will be finding out. You will basically compare the empirical probability with the observed values. First you arrange the values from lowest to highest. Suppose your I equal to 1 to that n, let they are already ordered. Then what will happen? You will find out probability that I think you will be like this, n minus I plus half, n minus I plus half, I equal to 1 to n, and this is the probability, empirical probability, cumulative probability basically, this is the cumulative probability. Then you have already that values are there, suppose x values are there, order values are there. So, you plot this with this and you must get a straight line. This is probability plot. Here what is happening in this figure you see?
If we simply take the errors and plot that histogram, then it will come
Histogram, what will happen, you will not get that from the histogram, you get a feel that okay, that may be normally distributed, but you cannot say 100% that it is normal or not. Similarly, probability plot is better than histogram here, but again probability plot also it is very difficult to know that what is the extent of departure. So, in that case you have to go for KS test, Kolmogorov-Smirnov test. Now, you see this probability plot given here. This is the residuals. See, residuals are arranged from lowest to highest. This is the ordered one, and this side the probability, that is basically cumulative part, percentage. So, if your n is 10, then the first one will be that is in the 5th percentile case, rest will be 95, will be rest the things. So, in that sense the first one is the 5th, 10th, then 15th, if number of observation is 10. So, in that way you are plotting here. So, you will get a straight line. If you do not get a straight line, then it says that there is departure from normality. For example, in this case last two values, that this value and this value plus first value, but little departure. I think this is not a gross departure. So, we can assume that they are normally distributed. Here again the subjectivity is there, that we are saying it is normally distributed, but quantitatively I think you can use Z Cartouche test is there, then your KS test is there, D max, all those things you can do. So, for the data set, normality test says that yes, data comes from normal distribution. Then autocorrelation, what we say, observations should not be serially correlated. For example, first observation vis-a-vis related with the nth observations or ith observation, that should not be correlated. It may so happen that over time if you collect something, there will be time lag. Maybe January data to next month January data, next year's January data, that will be, there may be the seasonal correlation. So, that type of case what will happen when you fit a linear model like ANOVA, then the entire non-linearity part will go to the errors. For example, you are fitting a linear model like this, but data is like this. So, ultimately you will capture this much, but this non-linearity part where it will go? It will go to the error. So, in this error domain that will be seen. And another issue what when I talk about that autocorrelation part, when you talk about, if there is correlation between the this observation vis-a-vis this observation, what will happen? This correlation part will not be captured here, but it will go to the error. Error will capture all those things which are not captured by the model. So, if I see the error observation order vis-a-vis the residuals, there should not be any systematic pattern. In this case, is there any pattern? Are you able to say that yes, there is a linear or non-linear or some increasing or decreasing trend? I do not think. It is a haphazard, random one. These are the observation in terms of your collection, observation first, observation second, observation third, like this observation order. If there is correlation, then what will happen? Suppose if your this side is residual and this side is your observation order. So, if your values are like this, what is happening then? They are correlated. Even if values will come like this, they are also correlated, but non-linear relation is there. This should not happen. It should be something like this. Nobody knows where it will be. So, this says that our data is definitely your independent. Then I think this one is autocorrelation, then we will go for independent test. In independent test, you are making the residual versus fitted values plot. Okay. Actually what happened in this case, same values for a particular fitted value, this is the fitted value, this is the value, you are getting like this. You will be getting like this because here it is our data is such that you will be getting at a particular point there are so many residuals values are there. But if you take large number of data, you will be finding out again no it will be filled up, all the total plot will be filled up by the data points. Okay. So, there is no pattern again, so no problem then, they are independent. So far we have discussed ANOVA, which is known as one way ANOVA. Getting me? One way ANOVA. Why one way? Because we have considered only different population in terms of one factor. For example, I say that different processes, we say that process A, process B, process C like this, and we treated them as if this is population 1, this is population 2, population 3. Now, what is the guarantee that the process will perform equally over the seasons? It may so happen that during rainy season the performance will be bad, then summer and winter, this is one. Second thing is that second issue may be, suppose the process operators, process A, process B, process C, A, B, C is there, but there will be different operator level 1, operator level 2 and operator level suppose your K. Mean who is actually operating the process, that also determine the quality of the process. So, in that case, in the first case or second case, what you require to do, you require to include the effect of operators, maybe the effect of seasons. Now, you do not have control on over seasons. So, even though you know, but you may be some action plan you may be taking, but on the over the that seasons you have no control. So, in that sense what will happen sometimes, suppose we can say that season is a noise variable, getting me, but you want to estimate the process effects keeping in view that the seasonal effects to be blocked. Getting me what I am trying to say? So, that means you will, one thing is that you go for rainy season productions and see the quality, summer production see the quality, winter production see the quality. That means you do not want the noise variable effect to be accumulated in the process effects. If you do like this, this type of design is known as blocking. So, this is one variable is block variable is there. So, rainy seasonal different, summer is different, winter is different. It may so happen that you have control over the operators. So, depending on the situation you may change the operator, you give the operator to different machines where he may be fit. So, in that case if you have control over the operator, so this process is one factor which is controlling the quality of the product produced, and as well as operator is another factor, that is factor 2. Even here also we can say noise variable, this is factor 2 and process is factor 1. Only difference between the first and second, this blocking and this is, in this case you are not interested to know, or you are not in a position to know this one. Better is you are not interested to know the seasonal effect because you do not have control on seasons. So, nullifying the seasonal effect or eliminating the seasonal effect, you want to estimate the process effect. Here you want to estimate both seasonal effect, operator's effect plus process effect. This type of design is, this is two-way ANOVA. This is two-way ANOVA. What will happen here? Why two-way? Because factor 1 having suppose A levels, that means factor 1 is having 1, 2 like up to A levels, factor 2 is having B levels, that means 1, 2 like B levels. Then your design is like this. What is your design? In this side you are writing factor A, this side or factor 1, this side factor 2, factor A or factor 1 and factor 2. So, factor 2 is having B levels, factor A is having A levels or factor 1 is having A levels. Okay. Usually we denote factor A or factor 1, factor B, A B is coming like this. Now, what will happen? You will collect data. Okay. So, factor 1 at level 1, factor 2 at level 2, you collect a large number of data, correct. Here also you collect some data, collect. So, everywhere you are collecting data. If I go by the population concept that what we have discussed in ANOVA, then what you are getting here? You are getting two important things. One is for factor 1 you will be getting here x, if I say this is L bar, I am giving one dot here. What is this? You can ignore factor 2. If you ignore factor 2, then the sum total of observations here, this cell, this cell, this cell, this cell, this observation is related to 1. So, you will be getting 1 average. You are ignoring factor 2. Similarly, here you are getting 2 average, like this here you will be getting A average. Now, you ignore A, you talk about factor 2 only, then here also you will be getting average. So, this one we are denoting like this x dot m, x bar L dot, L stands for all the rows here, that is labels for factor 1, x bar dot m, m stands for labels in factor 2. So, then this will be x bar dot 1, x bar dot 2. So, like this, I think this one x bar dot b, correct. Then here will be one grand average, yes or no? Grand average means I do not consider A or B anything or factor A 1 or factor 2, I will consider total, these are all my observations. So, it will be basically average of all the values given here. Now, as you have computed this XL bar here ignoring this factor 2, so can you not find out that tau L dot this minus grand? Similarly, here also you can find out, yes or no? I think we will not use this this one dot we will not use here, tau L, and similarly here we will use tau M. Then this one will be your x dot 1 bar minus x bar, x dot 2 bar minus x bar, like this x dot b bar minus x bar. This is known as two-way ANOVA. Getting me? Two-way. One factor 1 A levels, factor B, factor 2 B levels, and there is another issue is known as interaction between the factors. Now, what will be your ANOVA table in this case? In this case, your ANOVA table will be like this. Sources of variation. One is factor 1, factor 2 is also source, interaction 1 and 2 between factor 1 and factor 2, and error, then total. You have to find out sum square. So, it is I can write here sum square A I am writing for the first factor, second one I am writing sum square B. I think we should change little different, because B already for between we have taken for B. So, factor 1, factor 2, factor 2. So, if I write like this SS1 and SS2, no problem, then factor 2, then SS12, then it is SSE, and this will be SST. ANOVA case, it is always basically partitioning the observations into different components, similarly partitioning the total variability into the sources variability. Okay. So, here what will be the degrees of freedom? How many levels are there for factor 1? A level. So, A minus 1. How many levels are there for factor 2? B minus 1. What will be the interaction? A minus 1, B minus 1. What is the total number of observation? A B n minus 1, because see, if we consider that you are collecting n observation here, n observation here, everywhere n observation, there are A levels for factor 1, B levels for factor 2, there are A, B cells, and in each cells there are n observations. So, A, B, n. So, that is what is our capital N. Capital N is A, B, n. Now, if you collect different samples for different cells, as well as if you collect different samples for the factor 1 and factor 2 differently, ultimately this computation will be little different, but the you can still write n, you have to compute n. Okay. Then what will be the SSE's case? A B n minus A minus 1 minus B minus 1 minus A minus 1 into B minus 1, because total will be this. So, what will be this value? A B n minus 1 minus A minus 1 minus B minus 1 minus A minus 1 B minus 1. Okay. So, this is A B n minus 1 minus A plus 1 minus B plus 1. So, minus this is A B okay, minus A minus B plus 1, correct. So, I am writing A B n minus 1 minus A plus 1 minus B plus 1 minus A B plus B minus 1. So, plus A plus minus A plus B minus B minus 1 plus 1, then it is basically this is 1 minus 1 na? This is plus 1, this also cancelled out. So, that means A B n minus 1. So, your okay. Then what you require to know? You require to compute MS, mean square, that variability. This will be MS1 will be SS1 by A minus 1, MS2 will be SS2 by B minus 1, then MS12, that is interaction, which is SS12 by A minus 1 into B minus 1, then your MSE will be SSE by AB into N minus 1. Then you find out F. What will be your F? F basically the concept of F here is here, why we will use in this fashion F. What we want to see, that whether factor 1 variability explanation is more than the error or not, whether factor 2 is explaining equally to error or it is better, or interaction to error. So, that means every sum squares, here we will take the mean squares, will be compared with error. So, as a result, for this F1, if I say for the factor 1, this one will be MS1 by MSE. For factor 2, it will be MS2 by MSE. For 1 2, MS12 by MSE. These are the things you want to test. Okay. Now, what will be the degrees of freedom for this case? If this one greater than, what is our numerator degrees of freedom? A minus 1, and denominator degrees of freedom is AB into N minus 1. If this alpha, this is the case. So, if computed F is greater than the tabulated F, then what will be your decision? Reject H0. So, similarly, if this one is F B minus 1 A B N minus 1, do it. If this one F A minus 1 B minus 1, I think into A minus 1 into B minus 1 and A B N minus 1, then do this. This is what is known as two-way ANOVA. Now, you can go for multi-way ANOVA also. What will happen ultimately? Suppose you three-way ANOVA. What you will do? How do partition it? Three-way ANOVA case. Three-way ANOVA. That means, if I say factor, I am now writing in terms of ABC, factor A with A labels, factor B with B labels, factor C with C labels. So, if I collect equal sample size, suppose sample size is n. So, your total observation will be A, B, C, N, total observation that will be okay. Now, I will not compute anything, only thing I want to write here, what will be the sources of variation, sources of variation. Definitely first is A, second is B, third is C, then definitely AB, interaction between A and B, interaction between A and C, interaction between B and C, interaction ABC. Correct? See, first is A, second is B, third is C. AB may interact, AC may interact, BC may interact, and all three may interact plus error. So, your total variability will be decomposed into different sources. Now, A, B, C, these are all known as main effects. A, B, AC, BC, in this case this is 2 OA interaction effects. ABC is 3 OA interaction effect. And error. So, you have to find out SS, for everywhere you have to find out SS, then you have to find out DOF, degree of freedom. Degree of freedom is for main effect A minus 1, B minus 1, C minus 1, interaction effect A minus 1 into B minus 1. For AB, for AC A minus 1 into C minus 1, the like this ABC case A minus 1, B minus 1, you know, that multiplication, and your for your total case that will be ABC n minus 1, then the for error part just subtract. Once you get all those things, suppose SSA, SSB, SSC, SSAB, SSBC, SSAC, SSE, then SST with all degrees of freedom, you have to compute FA, FB like this, and you know that what will be the degrees of freedom for the tabulated value, that F value you calculate. This is what is the decomposition, and by this manner you will be able to find out the effect of many factors, their interactions. It may so happen that your case is such that there is no effect for B or C, but A, AB, BC, these effects are there. So, that interaction effects you have to control. Getting me? Any question you want to ask me? No question? I think now you are in a position to explain ANOVA for any number of factors.
So for 3 it is 8. For n it will be 2 to the power n.
Just to just compute little bit.
Including
For 3 this is 2 to the power k. Suppose I have
NC0 plus NC1 plus.
in that sense calculate, because it all depends, because 3 factors and how many main effects? 3 main effects. How many interaction effects? So, that means NC1 is coming, then 2 at a time, NC2 is coming. So, okay, that way you will calculate. Because 3 factors 2 at a time, 3 factors 3 at a time, 3 at a time will be 1, 1 at a time will be 3, and 2 at a time will be another 3. So, that sense it is coming. So, you calculate, this is okay. Bolo? You ask me some question? It's okay na? So, this is basically the totality from ANOVA point of view. I think ANOVA is very useful, very powerful technique also, and you find out in many cases ANOVA is required, but this is a univariate model, keep in mind. In the multivariate counterpart is MANOVA. So, we will discuss in next class. MANOVA will be discussed in next class. And for ANOVA, I suggest you to follow D.C. Montgomery, Design and Analysis of Experiments. This is the best book I have read in terms of your ANOVA. Large number of real life examples are given, and if you know ANOVA, MANOVA will be extension to the multivariate domain. Little bit computational difficulty will always be there, because you will be computing in the matrix domain. This all sum square will become, that also you have seen the matrix domain. Sum square will not be there, it will be SSCP, sum squares and cross product. Okay, okay, thank you very much.